Hi! If this is your first time here and you're wondering why, since all the other videos on my channel are in Italian, well, this is an experiment and you're part of it. If you bear with me to the end, I will explain everything. Let's get started. I'm Cuso, and this is La fisica che non ti aspetti. At the end of September, an article was published on Nature by the title Observation of the Effect of Gravity on the Motion of Antimatter. Other online articles came up with even more curious titles. Antimatter falls down, not up. Experiment at CERN confirms theory. What exactly are they talking about? Let's take it one step at a time. In the meantime, I will premise that I have already covered many of the topics I will touch during this video in greater depth in the historic series on the Standard Model, the best theory of particles, which, unfortunately, is all in Italian. For now. Here I will limit myself to a super summary, but I will link everything again in the description. As it happened in the past already, I set out to write the text for this video, and doing a bit of research I stumbled upon one of the authors who very kindly gave me some very useful information. So I thank Professor Germano Bonomi of the University of Brescia, who worked on this experiment and with whom I had an interesting conversation on Zoom. But let's get down to business. The matter of which everything we see is made, including ourselves, is called baryonic matter. It is basically matter made up of atoms. This means more specifically matter made up of three kinds of fundamental particles: electrons and two kinds of quarks, up and down, the particles protons and neutrons are made of. But the Standard Model describes many other elementary particles, for a total of 6 leptons, including the electron, and 4 other flavors of quarks. In addition, there are the particles that mediate fundamental interaction, excluding gravity, which are called gauge bosons. But all of this interests us relatively. In 1928, Paul Dirac wrote a paper in which he hypothesizes the existence of another kind of matter that had very peculiar properties. In short, every known particle is associated with another particle that has all charges of equal value, but opposite sign. And remember, all charges. For example, the electron has not only an electric charge, but also a weak charge, since it is subject to the weak force. Quarks have a charge called color charge. Here, this particular particle has all the charges reversed, and for this reason it is called an antiparticle. That's all right about the charge, or at least I hope so, but there is another aspect to consider. What about mass? Experimentally, it was soon observed that Dirac's idea of an antiparticle having an inertial mass identical to that of the corresponding particle was correct. This means that if I apply a force to an antiparticle, it will undergo an acceleration entirely analogous to that of the corresponding particle. As an example, let us take Lorentz force, that is the force to which electrically charged particles are subject when they move in a magnetic field. The intensity and direction of the force depend on several factors: the strength of the magnetic field, the velocity of the particle, the angle formed between the velocity and the magnetic field, the inertial mass of the particle, and its electric charge, including the sign. The effect is a deviation from the initial trajectory, so two particles that have opposite charges are deflected to opposite directions. If they also have the same inertial mass, the magnitude of the deflection will be equal, which is exactly what happens for a particle and its antiparticle. I would say that we are still in the realm of the understandable, but now we have to take a somewhat tricky step. In formulating the theory of general relativity, Einstein enunciated the so-called equivalence principle, according to which the inertial mass and the gravitational mass of a body are precisely equivalent. But Einstein was necessarily talking about ordinary matter, since antimatter would have been theorized at least 13 years later. Does the equivalent principle also apply to antimatter? In other words, does an antiparticle experience the effect of gravity in exactly the same way as the corresponding particle? Does a positron fall down when it is in a gravitational field? Let us make one thing clear. There are relatively few physicists who, while proposing models of gravity alternatives to general relativity, thought it was possible that antimatter undergoes repulsion by the Earth's gravitational field. But if we want to be fair, no one has ever, at least until a few weeks ago, proved that this is not the case, nor that the equivalence principle applies strictly to antimatter as well. The difficulty in proving something seemingly so obvious is that antimatter is extremely rare, because it is unstable. If an antiparticle meets its particle, it tends to undergo a process known as annihilation that causes their immediate disintegration. So, once an antiparticle has been created, and at CERN they are particularly good at doing that, it must be isolated from everything, or you risk losing it in a flash. Literally. In addition, the particles that are most frequently created are electrically charged, so they are subject to electromagnetic fields, which alas have much more intense effects than gravity. So an antiparticle or an antisystem must be found that is electrically neutral to at least rule out the effects of electric fields. It would be wonderful to have an antimatter stone and be able to just drop it from the Leaning Tower of Pisa to measure its acceleration of gravity, but alas, Galileo has to give up this experience. What did the alpha experiment conducted at CERN succeed in doing? Let's start with the choice of the antiparticle, which is important, an antihydrogen atom. This is an entity consisting of an antiproton around which is an antielectron, the exact counterpart of a common hydrogen atom. These antiatoms have already been studied at CERN to see if their energy levels are the same as those of ordinary hydrogen. On the surface, this should be obvious, since the Schrödinger equation does not in fact change. But proving it experimentally is a mess. Alpha does an extremely complicated thing, but let's try to take it one step at a time. Once antiprotons and antielectrons have been produced, since they are both electrically charged, you can enclose them in a trap consisting of electric fields, thus forcing them to interact with each other and form the antihydrogen atoms, which are then electrically neutral. The antihydrogen atoms are no longer affected by static electric fields, but having a magnetic dipole moment, they can feel magnetic fields gradients, and it is by exploiting this characteristic of theirs that the experiment can work. The heart of alpha consists of a vertical magnetic trap. Antihydrogen atoms are locked inside it and are trapped by a magnetic field gradient that acts somewhat like a cap, both upwards and downwards. By varying the intensity of these two barriers, it is first possible to select the coolest atoms from those available. Oh yeah, I forgot. These atoms are not stationary, but constitute a gas and therefore travel this way and that in all directions, just like air molecules. So you will also see atoms going upwards, but not because of who knows what anti-gravity, but just because their velocity vector is casually directed upward. By selecting the coldest atoms, whose maximum kinetic energy corresponds to a temperature of just 0.5 Kelvin, you greatly limit their agitation. And what would one expect to observe? In the absence of the two caps, the atoms should emerge quite freely from both the top and the bottom, but with a preference for the bottom. This is, at least, if they are actually subject to gravity, like baryonic matter. What was done during the experiment was to play with the intensity of these barriers, to try to have as many conditions as possible. When the bottom barrier was much more intense than the top one, and this magnetic field bias is measured precisely as a difference in equivalent gravity accelerations, the atoms all escape at the top. When it is the low one that is very weak, they all escape downward. This happens precisely because their agitation causes them to move in random directions. Particularly interesting are the cases in which the upper barrier is weaker than the lower one by 1 acceleration g, and the one in which the two barriers are equal. In the former case, the number of atoms is practically identical between the two ends, and in the latter, the number of atoms escaping from the lower barrier is higher. And this happens precisely because the antiatoms are subject to gravity and tend to fall downward. And how do we count how many anti-hydrogen atoms have escaped from either end of the trap? Simple. You crash them against the physical walls of the trap container and observe the trail of a particular type of particle, the pions, which are byproducts of the annihilation process. And what was the result? As I have mentioned already, it has been observed that indeed more atoms come out of the lower mouth. So, anti-gravity? We can forget about it. Also, going to look at the gravitational acceleration they are subjected to, it is observed that this is, despite rather large errors, similar to that to which baryonic matter is subjected. It is certainly not definitive, proven proof that antimatter is subject to the same gravitational attraction as baryonic matter, or that the equivalence principle applies exactly to it as well. But it is certainly a step forward in understanding this alternative phase of matter that almost 100 years later still holds many surprises. The authors quote in the final part of the article's abstract, "Where pulses anti-gravity has been rolled out. This experiment paves the way for precision studies of the magnitude of gravitational acceleration between antimatter and Earth to test the WEP, the weak equivalence principle." This video is coming to an end, but as promised, let me explain what this experiment is. For the past few months, some of my colleagues abroad, and my job has nothing to do with science communication, complained that they could not understand my videos although they thought they could be interesting. So, after loading this video in Italian, and given the fact it was surprisingly well received, I decided to give it a try and translate it in English. It was a rather easy thing, thanks to online translation services. In their mind, translating videos in English would extend my potential audience. It is certainly true, but since I don't feel like leaving my Italian community behind, I'm thinking of loading two versions of my video from now on, an Italian and an English one. And if you see some topic in the old videos you find interesting, let me know. I may consider translating them as well. Well, this is all for now. See you soon, I hope. Kuzo out.